Assalamualaikum warahmatullahi wabarakatuh and good morning. Today my group will present about a metal organic framework. My name is Fatin Shami binti Zainuddin. My metric number is 93986. This is our content. It has 5 items and I will continue about the structure. The metal organic framework structure is a class of a compound consisting of metal ion or cluster coordinated to organic ligand which can form 1, 2 or 3D dimensional structure. It also can be defined as an organic-inorganic hybrid crystalline and porous material that consists of a regular array of positive charged metal ion which is surrounded by the organic linkers molecule. Because of this hollow structure, MOF have extraordinary large internal surface area. So it has various applications that have been developed that exploit due to this cage-like structure, such as gas storage and separation, liquid separation and purification, electrochemical energy storage, catalysis and sensing. How is the structure of MOF is built? The structural characteristics of the MOF are mainly determined by the nature of the metal center and also the organic linker. During the synthesis of this material, solvent and counter ion also play an important role. The counter ion change the environment of the metal ions and may generate the overlap with the structure that resulting in the weak interaction of the MOF. Solvent molecules also will crystallize during the synthesis and modifying the pore size. As we know that the transition metal play as the important compound that can generate wide range of structure. The properties of this metal, including the oxidation state and coordination number, can produce different types of geometry. In the formation of the MOF, the organic linkers must have a certain requirement, such as coordination number that usually have a multidentate that at least have 2 donors atom or being natural or anionic. Structure of the MOF is also affected by the shape, length and functional group present in the organic linker. So the structure of MOF is depending on the organic linkers also in order to produce a different types of internal storage and also the shape of the MOF. Bindings of the linkers to the metal center might generate different types of dimension, depends on the metal center. 1D have 2 ligand molecules are connected to the metal center to generate a chain. For the 2D, usually it use 3 or 4 molecules of organic linkers connected to generate a plane. 2D, usually the metal center with a high coordination number join 3 or more linkers molecule along the 3D dimensions. Okay, this is how we will build for the MOF. As you can see, they have different types of geometry of metal ions and also the different types of multidentate linkers. For the 1D, usually can produce a linear type. For the 2D, it will produce a plane type, and for 3D, usually will partial arrangement types. So this is an example for the 1D. As you can see, that produce a linear type of 1D. This is an example of the compound. Or for 2D is have a plane types which have 1:2 ratio of the ligand and metal center in order to form the 2D dimension structure. And for 3D type, you can see that it have a different or higher type of coordination number of the metal in order to form the structure.
Zafiri, my metric number is 191394. I will continue my part, which is MOF chemistry. How MOF is constructed. MOF can be constructed by combining inorganic polynuclear clusters, which are known as secondary building unit, with organic linkers through strong bonds. The bond between the linkers and secondary building unit are chemical, most reactive portion of the framework that can make the center of many post-synthetic modifications. The chemistry of secondary building unit not only allow us to redesign the MOF, but also it shows the thermal and the chemical stability of the metal oxygen bond, and also the reduction potential, kinetic inertness of the metal center, as also the stability of the overall structure. So these are examples of the secondary building unit as shown here. Triangular, square, tetrahedrohexane react with a ligand to form these examples. The first possible synthetic modification was carried on the secondary building unit in MOF is through open metal site reaction, which is coordination between unsaturated metal center within the secondary building unit by removing neutral thermal ligand, and is applicable for a wide range of secondary building units. The features of the metal open site is they have large unoccupied orbital, and their Lewis acidic nature gives rise to Lewis acid-base chemistry. So they have high activities in acid catalyzed reactions, so there will be strong interaction between the gas and the host. Open metal sites can be synthesized by heating them off. They are built from secondary building units that be neutral terminal ligands under dynamic vacuum must be neutral ligands. The post-synthetic modification, which is carried on the secondary building unit when the modification needs stronger interaction, ligand and linker exchange reaction can be used, which includes the substitution of the charged ligand and the formation of heterometallic secondary building unit. So the methods used are coordinative alignment, molecular retrofitting, and also structural robusting of the SRS intermediate impaired by rigid secondary building unit. As shown here, A is a Cal method. The capping format ligand on the octanuclear, the MOF 520, shown at the right side, can be exchanged with molecules that bearing appropriate binding group. In this example, the appropriate binding group is just monic acid as shown, and the molecule becomes MOF2,5-TTGA. So it's a chiral framework which is known by X-ray crystallography. As for B, it is in similar manner as A, but the MOF520 as shown in the middle has been transformed into MOF 250 BBDC, which is ditopic linear as shown in the middle, which is this is a reaction called molecular retrofitting. And lastly, as shown in the C modification done to enhance the mechanical stability. And in this example, the structure as shown at the beginning at the left, PCU topology has been transformed to SRS framework in the middle, and the right one, it becomes PCU again after adding metal ions and linkers. It can be synthesized by merging the ligand into the MOF by using sulfate-assisted ligand incorporation, and it's achieved by treating the MOF with excess of ligand. And this process allows the replacement of the terminal ligand by functional molecule, but must have appropriate site and the geometry so the reaction can happen. The guideline for the metal ion exchange is first, the secondary building unit that undergo cation exchange are often currently unsaturated, and also the secondary building unit from saturated metal can undergo metal ion exchange, but must be started more dynamically unstable or kinetically labile. And also the structure of MOF may influence the rate of ion exchange. It depends on the easiness of structural deformation. And lastly, the periodic tense is experimentally showed that Cu copper to plus may replace the second row transition metal such as cadmium to plus. Its synthetic pathway, the MOF is soaked in DMF with appropriate metal salt for a period of time, and the metal exchange will happen through the postkinetic ion methanolysis and oxidation.
Assalamualaikum and hi, my name is Hidayah binti Hassan. My metric number is 194777. So I will continue the presentation on the properties of metal organic framework. The first one is MOF has high durability, which means that the material have the characteristic which to withstand high pressure or damage. This can be proved by research, which it shows that the encapsulation of polymer chain into MOF can effectively prevent coordination bonding breakage in MOF, and it can also withstand the high pressure. So the hardness of a single MOF can be greatly improved This can be proved by using nano-imputation analysis, which it depends on the direction of the inserted polymers. So the addition of the polymer chain will not affect the crystal structure of the MOF, which means that we can really depend on this method in order to improve the mechanical properties of the MOF. So you can see at the below, which show a figure 1 schematic illustration of improvement of the mechanical strength by polymer insertion. At the left hand side, we can see that when we apply pressure without a polymer insertion, the structure of the MOF will not maintain. While at the right hand side, when we insert the polymer and we apply the pressure on the structure of the MOF, it will maintain. So this shows that when we insert the polymer into the MOF structure, it will improve the mechanical strength of the material. Second one is the high surface area and large pore size. So they have an internal surface area is a result of the atomic components. So metal atoms linked together by organic molecules forming a cage-like structure. So this MOF design was have a challenge because due to the significant number of possible structures. Studies have shown that large pore size, high surface area, or high pore volume are not becoming advantageous for application involving small gas molecules. So you can see the schematic illustration of a metal organic framework. So it consists of a metal ions and organic ligands, which has a highly porous material with an ultra-high surface area. So the various structure of MOF can be synthesized depending on the kinds of metal ion and also organic ligands. So the third one is high porosity. Porous is a material that is easily absorb fluids or allow liquids pass through. Porosity can be increased to increase the capacity of MOF gas absorption. When more porous structure will have a higher surface area and hence more gas absorption size. So the method to achieve this goal is to use a longer linker length, which to expand the structure of MOF. Longer links have already been shown to lead to increased surface area. So when we increase the organic linker length, the accessible surface area can also be increased. So this will lead to an increase in the number of absorptive sites as more exposed phases and gas absorption edges are present. So you can see the graph when we increasing the linker length, so the surface area also increase, which means that the number of absorptive sites can also increase.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Syafiqah Izwana binti Muhammad Zahari, and I will proceed with synthesis of MOF. In here, we have 5 types of synthesis of MOF. First is solvothermal synthesis. Second is mechanochemical synthesis. Third is electrochemical synthesis. Fourth is microwave and ultrasound assisted synthesis. And finally, near supercritical water condition synthesis. Solvothermal synthesis. The synthesis comprises the reaction of the metal salt and the organic ligand in the presence of organic solvent or solvent mixture typically involving formamide, alcohol, or pyrrolidons. The reaction temperature is usually considerably less than 520 K, but it depends on the boiling point of the solvent used. For example, if we use methanol, the synthesis temperature will be 338 Kelvin. Upon heating, the blends in sealed container, such as Teflon or gas pressure tube, will produce the compounds incorporating solvent molecules in the pores of the material. The organic solvents are often toxic, carcinogenic, and dangerous to the environment. For example, DMF is one of the most commonly used solvent in the synthesis of MOS is contaminant, mutagenic, and toxic. Additionally, DMF decomposes when heated at high temperature for long periods and therefore it cannot be reused. The solvent used is water. The problem with a low or non-solubility of the reactant and the organic ligand will occur, where it will prevent the formation of coordination polymer. Other important parameters: temperature, concentration of the reactant, and the pH of solution. The advantage of this solvothermal synthesis is that it yields range from 60% to 95%. The disadvantage is removing the solvent molecule occluded in the pores of MOS is not simple. It must be washed several times, which can take a few days and considerably reduce the performance. This table is the formulas and the condition of solvothermal synthesis of some MIL structure. Example and a picture of the solvothermal synthesis. Next, mechanochemical synthesis. It is named due to the chemical reaction that occurs as a consequence of mechanical energy supplied to the system. Through mechanical grinding process, several phenomena occur such as fragmentation of grains, generation of new surfaces, formation of dislocation and defects in crystal structure, polymorphic phase transformation material, and chemical reaction. Synthesis of MOF, metal salt and organic linker are ground together in the absence of solvent. For example, the synthesis of 1D copper coordination polymer. This is the example of the synthesis. Electrochemical synthesis. It was used to eliminate the use of anions such as nitrate, perchlorate, and chloride, which act as a counter-ion or as impurities in the network. In the synthesis method, the metal salts are replaced by metal ions produced from the anodic dissolution in the reaction medium. The solution also contains organic linkers indicated where metal deposition occurred. The advantage of this synthesis, material can be produced with high purity and ease of being industrially scalable. For example, is synthesis of Cu3BTC2. The copper metal bar that act as electrode, which can be anode or cathode, were employed in electrochemical cell with organic linker, which is BTC. It was dissolved in methanol with applied voltage between 12 to 19 volt and the current of 1.3 ampere for 150 minutes. As a result, oxidation of copper bar acting as anode forms Cu2+, while reduction of H2O at cathode produces hydrogen gas. The greenish blue precipitate will form. The example of the synthesis and the result. Fourth is microwave and ultrasound assisted synthesis. It is divided into two syntheses under this topic. For microwave, the reaction mixture is subjected to non-ionizing radiation, which does not change the electronic structure of material. Energy is supplied to the material by electromagnetic wave through the interaction of molecular type. The advantages of microwave synthesis: uniform controlled heating and great speed to generate the energy. The frequency of radiation must be between 300 MHz to 300 GHz. This synthesis is carried out in minutes and offers better method to control the morphology of material and the selectivity of phases. Example, synthesis of MOF5 at 368 Kelvin for 9 minutes with the yield of 27%, while synthesis using solvothermal method for 7 days produces yield of 60%. For ultrasound-assisted synthesis, it is another route for obtaining material where MOF with small crystal size will be produced in a short reaction time. The reaction mixture is subjected to ultrasound with approximately 19 kHz to generate high temperature above 500 K and pressure at specific location within the mixture. The increase in temperature and pressure are due to the phenomenon of cavitation, which involve creation, expansion, and destruction of small bubbles that appear when the reaction mixture is treated with ultrasound. In this case, acoustic radiation mechanical energy is converted into thermal energy. The example is MOF5, MOF177, and Cu3BTC2. Finally, near supercritical water condition synthesis. It is built for its acronym High Temperature Water HTW. in order to overcome the problem existed with the use of solvent. Due to these properties, HTW has been studied as a means of organic reaction, destruction of contaminants, and formation of nanoparticles. The water particle changed dramatically as it approached its critical point, which is 647 Kelvin and 220 bar. For example, the dielectric constant decreased to the value of typical nonpolar solvent. Thus, the organic compound such as organic ligand of MOF can be dissolved. The water can also be reused after the reaction completed, and ion exchange may be employed in order to remove the traces of unreacted organic ligand and the metal ions. HTW may be present difficulties due to the increase in the pressure and accelerated corrosion of reactors. This is the view of the crystal structure. So here is my references for my part. That's all from me. Thank you.
Hello everyone, my name is Shahmed Reza and my metric number is 186657. Today I'm here to present about the application of metal organic frame as a sensor. So first of all, what is sensor? Sensor is a particular object which can identify the physical properties of any particular element and also can give you the idea about the presence of that particular element in what level. So as you can see that our metal organic frame, which is NH2MiL53 aluminum, it is the name of this metal organic frame, which is used to sensing the hypochlorite ion in water. So why we need to sensing the hypochlorite ion in water? Because to monitor and control the free of drinking water from hypochlorite ion, and also to low level the free of hypochlorite ions which cannot kill the viruses and pathogenic bacteria effectively. And a matter of fact, higher level of presence of hypochlorite ion, which is ClO, can produce many disinfect byproducts which not degradable by human body. So how this metal organic framework work? We can see here written the mechanism is the strong fluorescence of aluminum nanoplates was significantly suppressed after the addition of free chlorine, and it is suggested that the energy transfer through the amino and hypochlorite ion hydrogen bonding interaction between the amino group and which is hypochlorite ions play a key role in the fluorescence suppression. Here you can see the diagram or working principle of the metal organic frame for sensing the hypochlorite ion. So how actually this sensor work? I say in a little bit of my understandable word, which is that when we are putting the sensor in water in open area or the under the sky or under the observation of sun, the chloride ion in the water can mobilize into the metal organic frame and enter through the nanoparticles to shorten their distance. Moreover of that, they can create a covalent bond between the amino and the hypochlorite ion, which actually create a bridge of our method to triggering the fluorescence quenching phenomena. So we can say that this particular metal organic sensor actually work based on luminescence but on quenching method, which means that higher energy state of electron absorbs the radiation and go back to their ground state. By using this sensor, we can know that how much of hypochlorite ion presence in the particular water. This is all from me. Thank you.
Hi, I'm Madam Binti Hassan and I'm going to explain the second example for the application of MOFs as sensors. So, for this example, H2 this example is the detection of Hg2 plus in water using ruthenium MOFs. Why? Because Hg2 plus is a heavy metal and has high toxicity and present risks to human health. So, how it is Hg2 plus is detected in water? So the luminescent tris-bipyridine ruthenium was stoked in an RUF framework and encapsulated in the pores of the MOF. So and then the RUMOFs exist as a precipitant in water. Exist in a yellow powder actually. So in the presence of Hg2+, the RUMOFs were rapidly decomposed by the Hg2+ ions, and then the large amounts of luminescent gas materials, in this case tris-bipyridine ruthenium, are released into the water, and this would give rise to strong fluorescence or electrochemiluminescence signals. So as this tris-bipyridine ruthenium was released, the water solution turns yellow and shows red light emission under the UV light. So as you can see here, when in the presence of Hg2+, this one is initially it only exists as this yellow precipitate, and when the Hg2+ is present in the solution, it decomposes the MOF here, releasing the Ru2 plus in the form of tris-bipyridine ruthenium, and this tris-bipyridine ruthenium will be released into the water, and it exists it emits red light under the UV. So in these pictures, it shows how selective it is, this MOF. As you can see here, in various types of anions, it doesn't show any color change, only except the Hg2+ here, and even when compared with its organic counterpart, this methyl Hg+ here, it doesn't show any change. So there is a potential that this ruthenium MOF can be used as a sensor to detect mercury 2+ ions in water, and this has been taken from this article down here. And that's it, the end of our presentation. Thank you for watching.
They are called metal organic frameworks, or MOFs. These materials are built from two different components. From the name is made out of metals, and that's one building block. The second building block is the organic linkers. And here we take advantage, it's like almost building Legos. You have different pieces that they come together, simple pieces, but at the end you could build very sophisticated structures. Imagine going down to the nano regime instead of dealing with Legos into the centimeters. So this is much smaller, but we deal with what we call self-assembly. What that means is putting everything in the reaction mixture. They find each other. We program them in a way to find each other in a specific fashion, and at the end you get one product at almost 100% yield. So this is the easiest way that you could construct very complex systems using very simple building blocks. And from there you could start thinking about, even if you have a small set of building blocks, the options and the number of possibilities becomes huge. But we don't rely on, let's throw them and see what we get. We program them in a way to come together in a specific manner.